Going through the solution to question 2 from the 2015 examination paper for numerical methods for partial differential equations. So question 2 presents you with Laplace's equation, which is the double derivative of the function u with respect to x plus the double derivative of the same function u with respect to y equals 0. And you're told that it's going to be discretized using 4 nodes. A 2D domain is going to be discretized using 4 nodes in the x and y directions, and such that the spatial step in the x direction is equal to spatial step in the y direction. And you also have Dirichlet boundary conditions, which means all these nodes on the outside, they're going to have a constant value indicated in the diagram. So these nodes in the middle, the grey nodes, these are what we're going to calculate the solution to. So question A, or part A, write down the Taylor series expansions of ux plus h and ux minus h truncation after the third order terms, and hence derive an approximation for the second order derivative. Okay, so the Taylor series, the general rule is it's h to the power n divided by n factorial multiplied by the nth derivative of u. So for example, h to the power 3 divided by 3 factorial, which is 6, multiplied by the third order derivative of u. Okay, so truncating after third order terms, which means we include the third order terms, and the truncation error is given afterwards. Okay, so ux plus h. Okay, to get ux minus h, we just replace h here with minus h. Where we have an even power of h, okay, the even power of a negative is going to be a positive, so just make sure you remember there's a positive at the even powers. Okay, to calculate the approximation for the second order derivative, okay, what we can do is if we add both of these Taylor series expansions, what's going to happen is this third order derivative here is going to get cancelled out, as is this first order one. Okay, so where you the odd order terms, when you add these two together, are going to cancel out. Okay, so if we add those together, then we rearrange to make uxx a subject, we get the second order symmetric difference. Okay, part B, show that the second order finite difference scheme for solving Laplace's equation is given here. Well, what we do is we take Laplace's equation and we approximate uxx using a second order finite difference, and similar for uyy. Okay, so there we have the x approximation. So notice that the h is now delta x, and we do similar for y. Also note that we're using ij notation here, where I is the index of the node in the x direction, and j is the index of the node in the y direction. Okay, well, it makes our life a lot easier since delta x equals delta y, so we don't have to worry too much about these terms on the bottom. Okay, so if we multiply out by the denominators, okay, all we have to do is rearrange to make uij the subject, and if we do so, we get this simple scheme. So simply the node to the north plus the node to the east plus the node to the south plus the node to the west divided by 4. Okay, part C, construct a matrix equation in the form of AU equals D. So U is going to be a vector of our U values, and A is going to be a coefficient matrix. So to do that, we take our finite difference scheme for each computational node in our domain. I'm going to apply that finite difference scheme, and I'm going to do it row by column order. So I'm going to go across the row before going up the column. Okay, so to do that, so we've got a quarter times the node to the north plus the node to the east plus the node to the south, which in this case happens to be the boundary node 5. Okay, so just that's that node, and then the node to the west, which has a value of 4. And if I do the similar for the other 3 computational nodes, I get these a system of 4 equations. Okay, and this is a linear system. If I transcribe this equation so that all the unknowns are on the left-hand side, I get these 4 terms here, which of course can be written as a matrix equation. Okay. Part D, explain why indirect methods are preferred to direct methods. Well, typically finite difference grids have a large number of nodes, and when you apply finite difference schemes, a lot of those nodes have a value of 0. Okay, so they're sparse systems, and essentially sparse systems are computationally inefficient when using direct methods, and a lot more efficient when we use indirect methods. Okay. Question E. For each of the methods listed below, write out the scheme for calculating Uij k plus 1. Now this k plus 1 means what is our value of our next estimate of the solution. Okay, so UK is the value of the current estimate of the solution. Now the Jacobi method is very simple. You just take the finite difference method and you put a k superscript on each of these. So this will have a k plus 1 superscript, and we're using the current value for each node. Okay, so there we have the Jacobi method. The Gauss-Seidel method, now this uses the most up-to-date information. So if we go in row by column order, I go back to if I've calculated U11 and then I go on to U21, I'm going to use my newly calculated value of U11. Okay. Likewise, if I'm at U12, I've already calculated U11 in the current iteration, so I'm going to use the most up-to-date values. So in short, any node which is to the west or to the south, I use the k plus 1 value there. So j minus 1 means a node to the south. The I minus 1 here means a node to the west, so I'm using most up-to-date values. Okay. Question F says, edit the program Laplace.m by replacing any question marks with appropriate commands to solve this problem using Jacobi and Gauss-Seidel methods and an error tolerance of 10 to the minus 6. Okay, so I'm just going to scroll up to the initial conditions. Okay, so here's just bringing in Laplace.m. Okay, so you can see here we have number of nodes in the x and y directions of 4, and I was asked to use a tolerance of 10 to the minus 6. Okay. Define x, y. We don't actually really need the x and y array here, so I'm just going to. Actually, no. I'll put it in anyway. Let's say. Say we're doing 0 in spaces of 1 up to 3. These aren't actually required in this particular example. And the initial conditions, well, thing to remember about the initial conditions is MATLAB, as you uses matrix index. Okay, so this is in matrices, this is node 1, 1, this is node 2, 1, etc. So what this means is we have to flip this upside down. Okay, so I'm going to start with the bottom node first, bottom row first. So we've got the 5s, and then the next row is going to be 4. And I'm going to use zeros as my initial starting values. 3, 0, 0, 7. And then we have 2, 4, 6, and 8. Okay, so those are my initial values for my solution array. Okay, if I scroll down. Okay, so it's asking me now to enter in the methods. So I'm going to start with Jacobi. Okay, so that's 1/4 multiplied by the node to the north, plus a node to the east. Oh, straight away I made a mistake here. Notice the index goes J then I, because again we're using matrix indexing. Okay, so I almost made a mistake there. So the node to the north. So the clue is in the JI there. And a node to the east, plus the node to the south, so that's j minus 1, plus the node to the west. Okay, this is the Jacobi method. Remember, it uses the current values, so these are your UK values. Okay, so just check there's no other question mark. So if I run that code, yeah, it's run here, and I just bring in the command window. So you can see the Jacobi method took 24 iterations, and it's converted to this solution. So what we've got 4.6 recurring, 5.3 recurring, 4.3 recurring, and 5.6 recurring for our solution. Okay, so that took 24 iterations. Okay, let's do the similar But this time I'm going to do the Gauss-Seidel method. So UK plus 1 JI. Okay, so it's very similar, but this time remember that the node to the south and the node to the west use the most up-to-date value. So it's a very minor change to the Jacobi, but it makes a big difference to the convergence. UK plus 1. Okay, right, so that's Gauss-Seidel, and I run that, and I just bring it in the solution, and you can see only taken 13 iterations. And notice the solution's the same, so we'll still get the same solution, but it just got there a lot quicker. So 13 iterations as opposed to 24. Okay, so if I just go back to the solutions. So I've written down the solution that the question asked me to do, write down the solution for the computational nodes correct to 4 decimal places. Okay, so I don't need to write down all of them. Okay, I'm only writing down the final solution. And so the Jacobi method took 24 iterations, and the Gauss-Seidel method only took 13.